Okay, in this part we are trying to look at some geometric interpretation of quadratic forms. So in general, when you're trying to investigate a function f of x, right, let's say you have the form of the function, often it's very interesting, especially if you have a function of many variables, to actually look at what are all the possible values of the variables. So let's say you have two variables x1 and x2. What are all the possible values of the variables that will give you a function value of 1, for example, right? So they're essentially like level curves, right? You try to look at all the possible values of x1 and x2 that will result in the function value being 1. Okay, what are the possible values of x1, x2 that will result in the function value being less than or equal to 1, greater than or equal to 1. These are all the questions that we can ask to better understand the geometry of the function that we are dealing with. So here, for example, we are dealing with, let's say, quadratic forms. Here x1 square plus x1 x2 plus x2 square, and we are interested in understanding what are all the possible values of x1 x2 for which this value x1 square plus x1 x2 plus x2 square is equal to 1. Okay, and we want to do this in the most general way possible, not just for this specific example that we have given over here. Okay, so how do we try to understand the geometry of this, right? So let's go back to the general formulation x transpose ax equal to 1. This is what we are trying to do. We are trying to find all x such that x transpose ax is equal to 1. Okay, now A is symmetric, as I said before. We are going to assume that A is symmetric, and by the spectral decomposition theorem we had actually written that this is the same as y transpose lambda y is equal to 1, where y is equal to q transpose x. Okay, now y transpose lambda y, as we said before, is just going to be a sum of squares. So it's going to be lambda I yi square I equal to 1 to n is equal to 1. Okay, so this is an expression now that is much easier to understand geometrically. For example, let's take the scenario when n is equal to 2. Then you will just have lambda 1 y1 square plus lambda 2 y2 square is equal to 1. Okay, and this in the y1 y2 plane is actually very easy to interpret. For example, let's take a simplistic scenario to understand. What if lambda 1 and lambda 2 were both 1? Okay, lambda 1 and lambda 2 were both 1, then this just becomes y1 square plus y2 square is equal to 1, which is simply a circle, right? So it is just going to be a circle in the y1 y2 plane. Okay, so I hope it looks okay. So it's just a circle in the y1 y2 plane, right? So this is just your y1 and this is just y2, and this is just one circle of radius 1 inside that, right? So this is of course y1 y2, but when you want to go back to x1 x2, remember that they are related by y equal to q transpose x. That's essentially going to be a rotation, right? And a rotation will not really change a circle, so you'll actually get a circle even in the x1 x2 plane. Okay, but now let us take the scenario, maybe lambda 1 is like 1 but lambda 2 is 2, right? Then you will get something like y1 square plus 2y2 square is equal to 1. Okay, and this will actually look like an ellipse. Okay, so this is going to be an ellipse with the major and minor axis still being the okay, so which so this is going to be an ellipse. Is going to be elongated along the y1 direction, or is going to be elongated along the y2 direction, right? It's going to be elongated along the y1 direction, so it's going to look something like this. Not really. So my drawing skills are up to. Okay, fine. Hopefully that's right. Okay, so it's going to be elongated slightly along the along the y1 direction rather than along the y2 direction, because y2 comes with a bigger coefficient here 2. So you can easily see, right, if we set y1 equal to 0, then the value of y2 that you get is going to be 1 over square root 2. But if you set y2 is equal to 0, you can get the value of y1 to be 1 or minus 1. So this is just going to be 1 comma 0, and this is minus 1 comma 0, and this is going to be 1 over square root 2, sorry, 0 comma 1 over square root 2, and this is 0 comma 1 over square root 2. Okay, so you can see that this is an ellipse, right? Now what happens if you go back to the x1 x2 plane from the y1 y2 plane? Remember that this is going to be some sort of a rotation. So in the x1 x2 plane, it's actually going to look like a rotated ellipse, right? So this is an ellipse here in the y1 y2 plane with major and minor axis both along the horizontal and vertical axis. But when you go back to the x1 x2 plane, you will actually get an ellipse whose axis essentially are not the horizontal and the vertical axis, but it's going to be an oblique ellipse. Let's just draw it for the sake of completeness, but all of you understand exactly what I mean. Okay, so it's going to be something like this, right? And the directions of this ellipse, the directions of the major and minor axis, here are essentially going to correspond to the columns of Q. Okay, so this corresponds to the eigenvectors. Okay. The ellipse is going to be more elongated in the direction of an eigenvector that has a smaller eigenvalue. Okay, so wherever the eigenvalues are small, that's the direction the ellipse will elongate more. Okay, in the this, for example, this direction corresponds to the eigenvector that has the largest eigenvalue, and this direction corresponds to the eigenvector that has the smallest eigenvalue. Okay, so you can see that essentially the geometry is that of an ellipse. So even in n dimensions, if all the lambda i's, if all the eigenvalues are positive, then the quadratic form, the equation, the level curve of a quadratic form, okay, is an ellipsoid if all eigenvalues are positive. We'll come back to this once when we do positive definite matrices as well. Essentially, a positive definite matrix is a matrix whose eigenvalues are all positive. You have encountered this definition before, but essentially, positive definite matrices are closely tied to ellipsoids. Okay, sticking to the two-dimensional case, what if one of the eigenvalues is positive but the other is negative? Right. So what if you have something like lambda 1 is equal to 1, but lambda 2 equal to minus 1? Okay, then the equation that you get is essentially y1 square minus y2 square equal to 1, which is essentially an hyperbola. Okay, it's essentially a hyperbola. So in general, when some of the eigenvalues are positive and some are negative, in high dimensions you actually get hyperboloids. Okay, I leave it to you as an exercise to think about what happens when one of the eigenvalues is 0. So let us say lambda 1 is 1 but lambda 2 is 0, then what do you get? Okay, so essentially this talks about in the geometry of the quadratic forms. So in the next portion of the lecture, we are going to look at the question that interests us the most usually is what are the variables for which the quadratic form takes on the largest and the smallest possible